It's spring break, but we gotta march into more physics. Here's lab 4, circuits. The main purpose of this lab is to predict the behavior of some simulated circuits, specifically with resistors and capacitors. In our examples, the system will be the circuit and the surroundings will be everything else. And here's a quick preview of the results. The first fundamental physics principle I will be using in this lab is the node rule, and this states that the current flowing into a node must equal to the current flowing out of it, and this is a result of the conservation of charge. Next up is the loop rule, which states that the sum of all of the electric potential differences around a loop is zero, and this is a result of the conservation of energy. Now lastly, we got Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage that is across it, and it's formulated by V equals IR. Let's start by exploring charge and energy conservation in series circuits. We're given this diagram and told to predict two currents that would be measured by two different ammeters. Well, we have to consider that the current is same everywhere in a circuit, and to find it, we have to find the total resistance and then use Ohm's law. And by doing so, we find that the current is this. Now we can prove this calculation by simulating the exact circuit online, placing an ammeter, which is the device that measures current, where I1 and I2 can be read. And as we can see, the currents match what we calculated. There you go. Okay, but what happens if we reverse the connections to one of the ammeters? Well, nothing changes. As you can see, both of the currents remain the same. Next up, what happens if we replace one of the ammeters with a voltmeter? Well, this time, two things happen. First up, the ammeter is going to read 0 amps because the voltmeter has extremely high resistance, basically making this circuit an open circuit. And next up, the voltmeter is going to read 3 volts since there is no other voltage drop in the circuit. It's going to take all that voltage drop across it. So since we found the total current that flows through the circuit, we can now find the voltage drop across each different part of the circuit. Now, the only places we're going to see a voltage drop is if there's some type of load there, such as a resistor or of course a battery. Well, we can use the loop rule and Ohm's law to find the voltage drop at those locations as seen here. The graph here visualizes the voltage gain and drop as we go around the circuit. The batteries contribute to a voltage gain, while the resistors show a voltage drop, with higher resistances showing a more significant drop. And as we can see, the sum of all the voltages here sum up to 0, so this abides with the loop rule. Now, when we attach a voltmeter to the circuit, the ammeter reading doesn't change. Why is this? Well, the voltmeter has extremely high resistance, so almost no current flows through it, and thus has no effect on the path and speed of the electrons. Just when we thought we were done with questions, we got even more. What's next? We're going to now replace the voltmeter with an ammeter in parallel with the 100 ohm resistor. What will happen to the current through the other ammeter? Well, ammeters have very low resistance, so current will go through it instead of the 100 ohm resistor. This is going to lower the total resistance to 47 ohms, so using the loop rule, we're going to find that the current is going to be 0.06 amps, which is larger than before. And simulating this online, we find the same exact results. There you go. And another question, what is the resistance of each circuit element? Well, by using Ohm's law, but rewriting it in terms of resistance, and by assuming that a wire and ammeter have a 0 volts voltage drop across it, we find the following values. Well, this does not match our simulation, so did we do something wrong? No, this is just a rounding error, so everything is actually fine. Finally, time to switch things up and go to race car circuits, resistor capacitor circuits. What I did here was create a circuit, one for a 10 ohm resistor and one for a 20 ohm resistor that involves a capacitor, and then measured the time it took to charge the capacitor and discharge it. For the 10 ohm circuit, it took 10 seconds for each, and for the 20 ohm, it was about 20 seconds. Next, I graphed the experimental relationship between the natural log of the current voltage over initial voltage versus time in order to find the time constant, which is ideally found by multiplying the resistor and capacitor values. We see a linear relationship between the two, and our experimental value is pretty close to the predicted. In this lab, there were two major sources of errors. One was human error in trying to stop the stopwatch and the capacitor from discharging at the same time, and two was that online simulations do not accurately represent the real world scenarios. Now for our further discussion into the results, what would happen if we used an actual ammeter instead of our simulated one? Well, the actual ammeter would have resistance, and this would limit the total current in our circuit. Next up, what if we used an actual battery and no resistor? Well, with no resistor, our model would predict that the capacitor would charge instantly. However, actual batteries have internal resistance, so this would not happen. Thank you so much for your attention and have a great day.